So today we're going to tackle an algorithm that sits right at the very heart of why quantum computers are so powerful. It's called the Quantum Fourier Transform, or QFT. And honestly, if you can wrap your head around this one idea, you've unlocked the secret to why quantum computing could literally change everything. So let's start with a question. What in the world could your music library possibly have in common with an algorithm that might one day break the internet's toughest codes? I know, it sounds like a weird riddle, right? But the answer is this incredibly powerful idea that connects both worlds, the idea of deconstruction. Let's dive in. Okay, imagine you hear a musical chord being played. It's this rich, complex, beautiful sound, right? But you know, deep down, that it's not just one thing. It's actually made up of a bunch of individual, simpler notes. The real trick is figuring out the hidden recipe, which exact notes are in that mix and how much of each. That's the core idea we're going to start with.
Well, that recipe finder has a name. It's called the Fourier Transform. It's basically a mathematical machine that can take any complicated signal, like our musical chord, and tell you exactly what simple ingredients or frequencies it's made of. And look, this isn't some abstract thing from music class. This is the magic behind how your MP3 files are compressed, how MRI scans see inside your body, and even how your Wi-Fi works. It is everywhere. So how does the normal classical version work? It's called the Discrete Fourier Transform, or DFT, and you can think of it like it's trying to tune an old-school radio. It takes your signal and methodically checks for one single frequency at a time. It asks, okay, how much of this specific note is in here? It does a whole bunch of math, then it starts all over. All right, now how much of this note? It has to do the entire calculation again and again for every single frequency it's looking for. It works, for sure, but it is incredibly repetitive and painfully slow.
All right, so that's the old way. Now let's jump into the quantum version. The QFT does the exact same job. It finds that hidden recipe of frequencies. But, and this is a huge but, it isn't working on a simple list of numbers. It's working on a quantum state. And that, my friends, is a completely different ballgame.
It all starts with the building block, the qubit. You know a classical bit, right? It's just a light switch. It's either off, which is a 0, or it's on, which is a 1. End of story. A qubit, though, it's more like a spinning coin. While that coin is spinning in the air, it's not heads and it's not tails, it's kind of both at the same time. We call this amazing property superposition.
And this is where things get really wild. Because of superposition, the amount of information you can handle just explodes exponentially. Get this, just 50 of these qubits can hold over a quadrillion values at the exact same time. But there's a second secret weapon here, and it's called phase. You can think of phase as the precise angle or rotation of each of those spinning coins. This is absolutely crucial, because the QFT is so clever that it doesn't hide the answer in whether the coin lands heads or tails. No, it encodes the answer directly into those phases, into the way the coin is spinning.
So when you combine superposition, holding all the numbers at once, with phase, encoding the answer in their rotation, you get one of the most staggering, mind-blowing speedups in the entire history of computer science. We're not talking about a small improvement here. We are talking about a totally different scale of reality.
Let's put some real numbers on this so you can see what I mean. Imagine you have a signal with over 1 billion data points. For a classical computer, that is a huge problem. But for a quantum computer, you only need about 30 qubits to hold all that information. So how many steps does each one take to find the recipe?
Okay, the straightforward classical method, the DFT we talked about, it would need roughly 1 quadrillion operations. That's a 1 with 15 zeros after it. It's an astronomical number, almost impossible to even imagine.
Now, back in the 1960s, some brilliant engineers developed a clever trick called the Fast Fourier Transform, the FFT. It was a massive improvement, and it cut the work down to around 30 billion operations. I mean, still a huge number, but way, way more manageable.
And now, for the same exact problem, the Quantum Fourier Transform. Using just those 30 qubits, it needs only about 900 operations. No, not 900 billion, not 900 million, just 900.
This bar chart really says it all. I mean, look at it. The classical DFT bar on the left would be a skyscraper shooting off the screen. The much-improved FFT is still a giant tower. And the quantum bar? You can barely even see it. It's just a tiny sliver on the floor. That gap isn't just an improvement, it is an exponential chasm. This is what people mean when they talk about quantum advantage.
So you're probably thinking, wow, if it's that much faster, why don't we use it for everything? And that is the perfect question.
Because here comes the big quantum catch, a fundamental and kind of weird rule of the quantum world that makes everything so much more interesting.
The catch is something called measurement. So after the QFT runs, you have this beautiful, incredibly rich quantum state that has all the answers to your problem encoded in its phases. But the instant you try to look at it to read the answer, poof, the whole thing collapses. All of that amazing parallel information just vanishes, and you're left with just one single random result. And this isn't a bug in the technology, it is a hard and fast law of physics.
So what's the point? Well, here's the secret. The real power of the QFT is unleashed when you realize you can't use it alone. It's not the main event. It's a subroutine, an incredibly powerful tool that you use as one step inside a much bigger, much more clever quantum algorithm.
And the most famous example of this is the legendary Shor's algorithm. What it does is it uses the QFT's insane power to find one very specific thing, a hidden repeating pattern, or a period, inside a giant string of numbers. And it just so happens that finding that period is the secret key to factoring huge numbers, which is the lock that protects most of our modern internet encryption. Shor's algorithm is smart enough to use the QFT to pull out that one crucial piece of information it needs while ignoring everything else.
And you know, breaking codes is really just the beginning. It's the most famous application, but the QFT opens the door to solving all sorts of other problems that are just completely impossible for even the biggest classical supercomputers.
For example, chemists could use it to perfectly simulate complex molecules to design new life-saving drugs or create incredible new materials. Physicists could use it to finally understand bizarre quantum systems like high-temperature superconductors. All these problems have one thing in common: their complexity explodes exponentially. That makes them impossible for classical computers, but a perfect job for the QFT.
But okay, let's have a quick reality check. Building a big quantum computer that can actually do this stuff is incredibly hard. Qubits are super fragile. The tiniest bit of noise from the environment can wreck the whole calculation. That's called decoherence. The little operations we do on them, the gates, they're not quite perfect yet. And to do something big, like run Shor's algorithm to break encryption, we'd need millions of really high-quality qubits, and, well, we're just not there yet.
And that leaves us with the big ultimate question, doesn't it? The power of the Quantum Fourier Transform isn't in doubt. It represents a true exponential leap in what humanity can compute. The theory is solid, the physics works, the whole challenge now is pure, hardcore engineering. Can we build machines that are stable enough and big enough to finally unleash that incredible power on the world's hardest problems?